What if I told you that the so-called dark age of the universe may never have been truly dark at all, just invisible to human eyes? We're taught a simple story. After the Big Bang, the cosmos went black for hundreds of millions of years. No stars, no galaxies, only a silent blackout. But dark depends on who's looking. In Genesis, before the first "let there be light," there's a haunting line, darkness, over the face of the deep. And yet, the Spirit moves. Not emptiness motion, not nothing, a world without visibility. Now swap ancient waters for early space, a universe filled with hydrogen, threaded by dark matter, shaping a vast cosmic web, while our eyes would have seen only night. The light wasn't absent. It was stretched, shifted, whispered in wavelengths we couldn't sense. And that's the journey we're taking today. From the first instance after time began, through Planck's map of the afterglow, Hubble's deep stare into nothing, James Webb's infrared dawn, and radio ears listening in the Australian desert. If the early universe was never truly dark, only unseen, what else have we mistaken for emptiness in our own lives? Stay with me to the end, and together we'll learn how to see the deep move and watch the first lights break through the veil of darkness. Before we can watch the deep begin to move, we have to question the picture of stillness we have been quietly carrying for most of our lives. The story of a universe that simply goes black and waits for its first stars is one of those pictures. Clean, dramatic, and almost certainly wrong in the way that simple stories usually are. You have probably seen some version of it. The universe begins, there is a brief blinding flash of creation, and then a blackout, an empty stage. For hundreds of millions of years, no stars, no galaxies, nothing but a thin soup of particles drifting through a featureless night. Then, suddenly, the first stars ignite, and the cosmos finally becomes visible. It is a compelling image because it behaves like a good film cut. Bright scene, hard cut to black, long pause. Then the first light fades back in. Your mind knows how to handle this. Darkness here means nothing is happening. It means the story has been paused. The problem is that the universe does not care about our cinematography. When cosmologists talk about the so-called dark ages, they usually mean the period after the hot, glowing plasma of the early universe has cooled enough for neutral atoms to form, but before the first stars begin to shine. If you could somehow stand inside that universe with human eyes, you would see nothing at all. No pinpricks, no fuzzy smears, no Milky Way band hanging above you, just black, in every direction. It is easy to slide from that sentence into a much stronger one. No visible light, therefore nothing to see. Therefore, nothing of significance is happening. The mind compresses all of that cosmic time into a single word: before. Before structure, before story, before meaning. But step back and listen to the phrases we are using. Dark, nothing to see, blackout. They are all written from one very specific point of view. The point of view of a small mammal, whose eyes evolved under the yellow-white star of a very ordinary galaxy, sensitive to a narrow band of wavelengths that happened to trickle through the atmosphere of a small rocky planet. To those eyes, yes, the Dark Ages would have been absolutely black. To other senses, they would have been crowded. Even in this supposedly empty interval, the universe is full of neutral hydrogen gas, stretching between regions of slightly different density. Full of a cosmic background glow, light released when the universe was a few 100,000 years old, now stretched into microwave wavelengths by billions of years of expansion. Full of dark matter, an invisible mass component quietly pulling everything together. There is no pause button anywhere in that picture. Only a change in how visible the story is to one very particular kind of observer. Imagine you are in a room at night. You switch off the lamp. To your eyes, the room is gone. The walls, the furniture, the dust in the air, the motion of your own hand in front of your face, all of it dissolves into black. If someone told you, in that moment, that there was nothing in the room, it would feel almost true. There is no evidence of anything, except maybe the sound of your own breathing. Now, imagine that. In the far corner, there is a security camera with an infrared sensor. When you plunge the room into darkness, its view does not change. The couch is still there. The table. The plant in the corner. The faint heat outlines of your body as you move through the air. The room has never been dark to that camera. It has only been dark to you. The early universe is like that room. The dark ages are what you get when you tell the story only in terms of human eyes. Something similar has already happened to us once, and it did not involve the beginning of time. It involved a patch of sky so small and so unremarkable that, for most of human history, no one bothered to look at it twice. In the mid-1990s, astronomers took a space telescope, one orbiting far above Earth's atmosphere, and pointed it at a tiny square of sky near the constellation of the Great Bear. This patch seemed empty through ordinary ground-based telescopes. No bright stars, no dramatic nebulae, nothing obvious to reward the effort. They did something strange. They left the telescope staring at that same dark patch for day after day. They collected every faint photon that trickled in, stacking them, accumulating them, waiting. To human eyes, it was like staring at a blank wall in a darkened room. When they finally read out the image, the blankness shattered. Where there had seemed to be nothing, there were now thousands of galaxies. Tiny, colorful swirls and smudges, each one holding billions of stars. Some of them were relatively nearby. Many were unimaginably distant, their light having traveled for more than half the age of the universe to reach us. All of them had been there the whole time. Our instruments just had not been patient or sensitive enough to reveal them. Astronomers called that exposure a deep field. People compared it to looking at a grain of sand held at arm's length and discovering that inside it was a city. The metaphor is imperfect, but the emotional effect is right. A piece of the sky that felt like nothing was silently packed with things all along. That image should have cured us forever of the habit of equating unseen with non-existent. It did not. The Dark Ages still live in the popular imagination as a literal blackout between the hot beginning and the era of stars. Even when the story is told a bit more carefully, there is a subtle trap. You might hear that, after a few 100,000 years, the universe cools, neutral atoms form, and light is finally allowed to travel freely. This light is the ancient afterglow we detect today as microwave background radiation. After that, the explanation goes, the universe contains a kind of invisible fog of hydrogen, and nothing much happens until the first stars form a few 100 million years later. The language leaves you with an implicit picture. On one side, a bright, opaque universe filled with light that cannot get out. On the other, a dark, empty universe where light simply does not exist until stars switch it on again. There is an imaginary valley here, a trough of non-being. But the moment electrons settled into orbits around protons to form neutral atoms, the universe was not plunged into some metaphysical void. It was filled with radiation. Moving through space, it was filled with matter. Clumping under the pull of gravity, temperature, density, and motion were all still there, everywhere, all at once. If you could translate every wavelength of radiation into sound, the Dark Ages would not be silent. They would be a long, low, ever-changing hum. The question is not, was there light? The question is, which light? And to whom? Our eyes have access to a little slice of the electromagnetic spectrum. Not the highest energies, not the lowest, just a band that happens to be well suited for seeing under the star that warms our planet. Call it a narrow window in an enormous house. Most of the universe's history, especially its earliest chapters, does not bother to pass through that window. The light from the afterglow of the hot young universe has been stretched into microwave wavelengths. The signals from neutral hydrogen in the dark ages hum along at radio frequencies. Even the first stars and galaxies, once their light has been redshifted by cosmic expansion, often show up best in the infrared. From the standpoint of human eyes, this all looks like darkness. From the standpoint of an instrument tuned to those longer wavelengths, the dark ages are not dark at all. They are full of patterns. Fluctuations in temperature, tiny excesses of matter here and deficits there. The early version of the cosmic web that will later turn into filaments, clusters, and voids. The universe does not stop composing itself just because our eyes cannot follow the notes. When we call that long interval a dark age, what we are really doing is admitting the limits of our own participation. This is the era during which no stars are yet shining in the narrow band of light we evolved to notice. There is nothing for our particular kind of retina to grab onto. To us, it might as well be black. But nature does not organize its timeline around the sensory reach of one species on one planet, circling one unremarkable star. If anything, the dark ages are the time when the universe begins to commit to a shape. Those slight ripples in density, born from quantum fluctuations when the universe was still incredibly young, begin to grow under the influence of gravity. Regions that are a little denser than average pull in more matter. Regions that are a little emptier give up what they have. Dark matter, which does not emit or absorb light at all, collapses into an enormous three-dimensional scaffold. Neutral hydrogen gas flows along this scaffold, pooling in the gravitational valleys. The universe is not waiting for the first lights to switch on. It is already building their neighborhoods. Seen that way, the phrase cosmic dark ages starts to feel like a mislabeling. It is not an age defined by darkness in any absolute sense. It is an age defined by our inability, so far, to watch it directly with the tools that come most naturally to us. The deep field image from that so-called empty patch of sky is the closest thing we have to a warning label on this kind of language. A reminder that looks blank and is empty are very different statements. That nothing often turns out to mean below our detection threshold. 2-1. So, when we say that, after a few 100,000 years, the universe entered a dark age that lasted until the first stars formed after a few 100 million years, we should hear a quiet question hiding under the words, dark to whom? Empty for which eyes? Black, according to which definition of seeing? If the early universe was never truly dark, only unseen from our narrow window, then perhaps dark ages is less a description of the cosmos and more a confession about us. A name for a period where the universe was busy and luminous in ways we have not yet learned to register. And if that is true, then we are left with a more unsettling task than simply waiting for better pictures. We have to decide what we really mean by darkness in cosmology, and whether it is a property of the universe at all, or just a shadow cast by our limited ways of looking. If darkness is partly a confession about how we look, then distance is another one, written in light. Every time you raise your eyes to the sky, you are not seeing where things are. You are seeing where they were, and the farther you look, the older the universe becomes. We learn very early that nothing outruns light. We are told that it moves fast enough to race around Earth many times in a single second, fast enough to cross the gulf between the sun and our planet in only a handful of minutes, and still not infinitely fast. That small, stubborn fact turns the cosmos into something strange. Every view is delayed. Every glimpse of the outside world is already a memory by the time it reaches you. Stand outside on a clear day and look toward the Sunday. Do not stare at it, just feel the warmth on your skin. The light that is warming your face left the sun several minutes ago. A flare that erupts on its surface will only announce itself to you later. For a brief time, there is a gap between what the sun is and what the sun appears to be. At night, look up at the scattered band of the Milky Way. Some of those stars are close in cosmic terms. Others are so far away that their light has been crossing interstellar space for hundreds or thousands of years. A few might already be gone, their lives ended in quiet collapse or explosive death, while their last messages of normalcy are still on the way to us. When we finally see them vanish from the sky, they will have been absent for a very long time. Nothing about this feels exotic once you get used to it. We live every day inside this delay. You hear thunder after you see lightning. You read a message long after someone typed it. You listen to the voice of a stranger recorded years before you ever meet their face. The universe is not unique in this. It simply stretches the delay to scales our minds struggle to hold. Now take that ordinary fact and expand it outward. Imagine space not as a flat backdrop scattered with dots, but as a series of nested shells. Closest to you is the solar system, then the neighborhood of nearby stars, then the larger spiral pattern of the Milky Way, then the slowly thinning population of galaxies as you push your gaze outward. What makes those shells different is not only distance, it is time. Light from the moon takes only a little more than a single second to reach us. Light from the sun takes a few minutes. Light from the nearest big galaxy, Andromeda, has been traveling for roughly a couple of million years. Light from the furthest galaxies we can presently detect has been en route for well over 13 billion years, nearly the whole age of the universe. So when you look out, you are also looking back. The night sky is layered history. The farther you search, the younger the universe you are seeing. Close in, you find mature spiral galaxies, clusters, and filaments. Stars already old, planets already formed. Deep in the distance, you find galaxies in their awkward adolescence, irregular shapes, intense bursts of star formation, messy collisions. Push deeper still, and the galaxies begin to fade away. The universe is younger than any structure you are used to. At some point, the shells end. Not because the universe itself stops, but because the kind of light we can see no longer comes from anything at all. We reach a wall, not of matter, but of opacity. Beyond that wall, the universe was so dense and hot that light could not travel freely. It scattered constantly off-charged particles, like the light inside a cloud that never makes it out in a straight line. That wall has a name in cosmology, but the name is less important than what it represents. It is the moment, a few 100,000 years after the beginning, when the universe cooled just enough for electrons to be captured by protons, forming neutral atoms. When that happened, light decoupled from matter. For the first time, it could stream through space without being trapped in an endless pinball game of scattering. The photons released then are still around us now. They have been stretched by the expansion of the universe into long, cool wavelengths. Instead of the fierce glare of a young, hot plasma, they form a bath of microwave radiation with a temperature of only a few degrees above absolute zero. They come at us from every direction, almost perfectly uniform, with tiny variations in temperature that encode the earliest imprints of structure. We do not see this background with our eyes. We detect it with instruments built to be sensitive to those long wavelengths. When we map it across the sky, we are seeing as far back as light allows us to see, not to the beginning itself, but to a surface, like the foggy shell of a cloud, beyond which light cannot carry information in the usual way. The story of how we found this background is almost disappointingly mundane. In the middle of the 1960s, two radio engineers in New Jersey were testing a horn-shaped antenna designed for satellite communications. They kept picking up a faint hiss, a persistent noise that would not go away. They checked for loose connections, for interference from the nearby city, for military radar. They even cleaned out pigeon droppings from the inside of the antenna, just in case. The hiss remained. Only later, in conversation with cosmologists who had predicted such a signal, did they realize what they were hearing. It was not the sound of their equipment failing. It was the echo of the hot young universe, cooled and stretched into microwaves, washing through their instrument from the entire sky. They had stumbled, almost by accident, into evidence that the universe had once been denser and hotter, and that this history was still written, faintly, in the radiation around us. From that moment, the sky changed, whether people noticed it or not. Above the blue of daytime and the stars of night, there is a third sky, a nearly uniform glow at microwave frequencies, the oldest light we can directly observe. It does not care whether we call it a discovery. It has been there since long before Earth formed. If you could see this background the way you see clouds, the whole firmament would be filled with it. No constellations, no gaps, just a mottled pattern of warmer and cooler patches, differing by only tiny fractions of a degree. On that map, up and down lose their meaning. Every direction is earlier than you are. Now, between that ancient surface and the galaxies we observe with optical and infrared telescopes, there is a gap, a stretch of time during which the universe is filled with neutral hydrogen, slowly cooling and clumping, but not yet lit by stars. From the standpoint of our usual instruments, that gap shows up as a missing chapter. We see the afterglow. We see the fully written pages of galaxies and clusters. But the first paragraphs, the ones where the universe quietly sets its own stage, are hard to read. Astronomers sometimes draw this as a timeline. On the left, the opaque early universe, wrapped in its glowing fog. On the right, the busy, structured cosmos, filled with galaxies. In between, a dark band labeled with that familiar phrase, the Dark Ages. Not because nothing exists there, but because our main ways of seeing struggle to reach it. Remember that deep field image, the one from the empty patch of sky that turned out to be crowded with galaxies. There is a similar trick happening along the line of sight. When telescopes stare at a tiny piece of sky for many days, they gather light not only from different places, but from different times. The nearest galaxies in the image are relatively recent. The smallest, reddest smudges are ancient. A single photograph becomes a compressed history, layers of cosmic time laid on top of each other. The same thing happens with the cosmic background, but more starkly. That glow represents a single, thin slice of time, the moment when photons last scattered off matter in a dense early universe. When we observe it, we are seeing a spherical shell around us, a kind of horizon. Every point on that sphere is the same age, and every direction points backward to that early era. You are, in a sense, always standing at the center of a series of nested time shells. Not because you are special, but because that is what it means to observe from any one place inside an expanding universe. There is your present. Around it, shells of increasing distance and age. At the outermost visible edge, the faded afterglow of youth. Beyond that, not nothing, but a region that light, in the form we use, cannot yet describe to us. This is why cosmologists sometimes talk about telescopes as time machines. It is not metaphor in the usual sense. We cannot step through them and emerge in the past. But with each improvement in sensitivity, each extension to longer or shorter wavelengths, we peel back another layer of the onion. We see a little farther, which means we see a little earlier. The Dark Ages shrink, not because they are changing, but because our reach is catching up. And yet, no matter how powerful our instruments become, there will always be a horizon. There will always be a boundary beyond which we cannot see, because information is limited by the finite speed of light and by the opaque conditions of the very early universe. There will always be a surface where our look backward in time meets a wall. This is not a failure of technology. It is part of the architecture of the cosmos. It also means that when we talk about the early universe, we are always talking about a compromise. We have one direct image, the microwave background, with its delicate ripples. We have images of very young galaxies, close to 1 billion years after the beginning, from deep surveys with space telescopes. And in between, we have a wide, partially unlit hallway, where the lights in our usual band are off, but other signals move through. When you hear that astronomers are trying to see into the Dark Ages, this is what they mean. They are not trying to turn an actual nothing into something. They are trying to turn a region of limited visibility into one with more channels, to replace a single narrow strip of perception with a broader set of senses. In your daily life, it is hard to feel the weight of this. The stars overhead are pretty, but distant. The idea that they are fossils of different times does not change your morning commute or your conversations with people you care about. Still, there is something quietly radical in the realization that every faraway glint in the sky is already gone from the moment you reach for it. It complicates the idea of now. It stretches the idea of here. It reminds you that your present is stitched together from messages sent long ago, from places that no longer look the way you see them. For cosmology, This delay is not an inconvenience. It is the method. The only way to know how the universe was is to receive what it left behind. Photons, neutrinos, gravitational waves, the distribution of matter, all of them carry records of their past interactions, written in their energies, their directions, their patterns. When you look far, you are not catching the universe in the act. You are arriving late to events that have already unfolded. You are reading old mail. The Dark Ages sit in that picture as a missing batch of letters. We know from earlier and later correspondence that something must have happened then. We can infer, from the way the universe looks afterward, that matter clumped, that the first stars ignited, that radiation carved out bubbles in the hydrogen fog. We see the results. We do not yet have a detailed diary of the process. So we give that interval a name that reflects our own ignorance more than it reflects the state of the universe. We call it dark. We draw it as a black band. We treat it as a pause between the afterglow and the first galaxies. And then we point our instruments at it from as many directions as we can invent, trying to replace blankness with structure. To look far is to look back in time. To look at the early universe is to acknowledge that there will always be a horizon, always a before, that we can only reach by inference. Between the afterglow on one side and the distant galaxies on the other is exactly the territory we are talking about in this story. An interval that feels empty only because our ways of seeing have not yet been fully translated to it. And if the sky itself is a layered archive of delayed messages, then what we call darkness in that archive may simply be the pages our current eyes cannot read, not the pages that were never written. If the sky is an archive of messages sent long ago, then somewhere in that stack there is a first page that we cannot quite unfold yet. A page where the universe is young enough to be almost unrecognizable and old enough to have already made some decisive choices. When people say Big Bang, it sounds like a single moment, a firework, a flash, a clean origin. The phrase invites you to imagine a bright explosion throwing matter outward into empty space, like a bomb going off in a pre-existing room. That picture is wrong in almost every important way, but it is persistent because it fits the kinds of events we are used to. The early universe is not a bomb in a room. There is no room. There is no outside. What we call the Big Bang is the beginning of the expansion of space itself, everywhere at once, with energy and matter and radiation mixed together in conditions so extreme that our imagination mostly fails. Not because the physics is pure fantasy, but because there is nothing in ordinary life to compare it to. In those first instants, the universe is hot and dense, beyond anything a human body or even human language is built to handle. Particles and radiation are not separate actors in a calm environment. They are the environment. Photons scatter constantly off charged particles. Quarks and gluons, the constituents of protons and neutrons, move in a thick, seething plasma. There are no atoms. There are no stars. There is not even, in any familiar sense, structure. And yet, even here, the seeds of structure are being sown. Quantum mechanics, which usually rules the world of the very small, refuses to be quiet, even on cosmic scales. When the universe is that compact, tiny fluctuations in energy density appear and vanish, as they always do. But an additional ingredient makes them stick: the rapid expansion of space itself. In a short interval after the beginning, a period cosmologists call inflation, space balloons at a staggering rate. Those microscopic fluctuations are stretched, frozen in as small differences in density from place to place. Later, when the universe has cooled enough for gravity to work on those differences over long times, they will become the blueprint for everything. Galaxies, clusters, cosmic filaments, and voids. The pattern of slightly more and slightly less matter is already there, invisibly written into the hot plasma. After inflation ends, the expansion slows, but it does not stop. The universe keeps growing larger and cooler. Quarks pair up into protons and neutrons. In the first few minutes, those protons and neutrons collide and fuse, forming the earliest light elements, mostly hydrogen, with a smaller amount of helium and trace amounts of lithium. This is sometimes called primordial nucleosynthesis. The first time the universe arranges its building blocks into something more complex than individual particles. There is still no darkness in any ordinary sense. The universe is filled with radiation, with light at energies so high that the very idea of visible versus invisible wavelengths has not yet separated out in a useful way. Photons cannot travel far without bouncing off charged particles, but they are everywhere, all at once. For hundreds of thousands of years, this state persists in broad outline. The universe expands. The average temperature drops. Energy thins out. Matter continues to cool. The ratio of light to matter, though, remains enormous. For every baryon, every proton or neutron, there are billions of photons. This is not a world where light is scarce. It is a world where light is trapped. Eventually, a threshold is crossed. As the temperature falls, electrons no longer have enough kinetic energy to stay free. They can be captured by protons to form neutral hydrogen atoms. This process does not happen all at once, everywhere in the same moment, but spread out over a span of time. Still, cosmologists can point to a rough epoch, about a few 100,000 years after the beginning, when the balance shifts decisively from a plasma of free charges to a gas of neutral atoms. This shift changes everything about how light moves. In a plasma, photons scatter constantly off electrons. Their paths are short, tangled, and forgetful. Once most of the electrons are bound into atoms, the universe becomes transparent in a new way. Photons are no longer constantly deflected. They can travel long distances without being scattered. The glow of the early plasma is suddenly free to stream out into space. Those photons are the ones we detect today as the cosmic microwave background, cooled and stretched by the subsequent expansion of the universe until their spectrum corresponds to a temperature of only a few degrees above absolute zero. The pattern of tiny temperature variations across that background is a direct image of the density fluctuations at the time of last scattering, the moment when light decoupled from matter. From our perspective, billions of years later, it looks like a wall of light surrounding us in every direction. From the perspective of the universe at that time, it is simply the moment when the fog thins and the radiation can finally move in straight lines. You might be tempted to think of this as the first true sunrise of the cosmos. Before it, no light could escape. After it, suddenly, the universe glows. But again, that picture smuggles in our bias toward visibility. There was light before. There will be darkness after. The boundaries are not between existence and non-existence, but between different ways that matter and radiation interact. Once most atoms are neutral, something else becomes possible. Gravity, which has been tugging on matter all along, can begin to pull gas together without radiation pressure, constantly shoving back in the same way. The tiny overdensities imprinted during inflation have something to work on. A fluid of hydrogen and helium that can start to flow towards slightly denser regions, amplifying the contrast. In those denser regions, gas will eventually collapse enough to ignite nuclear fusion, and the first stars will be born. Between the moment when the universe becomes transparent and the moment when those stars switch on, there is a long stretch of time in which the main players are invisible to human eyes. Dark matter forming a skeleton of halos and filaments, neutral hydrogen gas flowing along that skeleton. Background radiation steadily cooling and sliding to longer wavelengths. This is what cosmologists call the first darkness. Not because the universe is empty, or silent, or paused, but because there is no visible starlight yet. The afterglow from the early plasma is still there, but it has been redshifted into microwaves by the expansion. It would not register on a human retina. The neutral gas does not yet emit strongly in the specific lines that would show up as bright features in our band of vision. From inside that universe, with human eyes, you would see nothing. From outside, with a full set of instruments tuned across the electromagnetic spectrum, you would see a great deal. This is where a satellite like Planck enters the story. Launched in the early years of the 21st century, it was designed to map the cosmic microwave background with exquisite sensitivity across the entire sky. By measuring tiny differences in temperature from one patch to another, down to variations of only millionths of a degree, Planck gave cosmologists a detailed picture of the anisotropies imprinted at the time of recombination. Those measurements told us the proportions of the universe's main components: ordinary matter, dark matter, and dark energy. They confirmed that the fluctuations we see in the microwave background have the right statistical properties to have arisen from quantum ripples stretched by inflation. They allowed us to trace a line, with some confidence, from the hot plasma era to the structures we see today. But Planck also made the darkness look different. Once you can map the peaks and valleys in the early density field, the 1,000 places where gravity will gather gas, the idea of an empty, featureless dark age becomes even less plausible. The blueprint is already there, in fine detail. The universe in its first darkness is not a blank page. It is a printed sheet waiting for ink to soak through. As soon as recombination has largely finished, photons decouple, but gravity does not. Dark matter, which outweighs ordinary matter by a significant factor and does not interact with light at all, begins to collapse into halos more efficiently. Ordinary gas, dragged along by gravity, falls into those halos. The dynamics are complex, a competition between collapse and pressure, between cooling and heating. But the broad direction is simple. Structure grows. There is a quiet tension in this interval. On one side, the universe is expanding, trying to thin everything out. On the other, gravity is pulling in, trying to clump matter together. In regions where the initial density is slightly higher than average, gravity wins by a small margin, and that margin grows over time. In regions slightly emptier than average, expansion wins, and those regions become the great voids. From our vantage point, that tug of war plays out in darkness, because the main actors are not yet luminous in the way we can easily see. The first darkness is the age when the universe is busy redistributing itself, sketching the outlines of galaxies and clusters in the language of mass, not yet in the language of light. By the time the first massive stars ignite, the universe has already done a vast amount of work. Gas has flowed along dark matter filaments into potential wells. Halos have merged, collided, and grown. Some regions have become dense enough for collapse to run away. Others have emptied out so thoroughly that they will never host a galaxy. We tell the story as if the light comes first, and meaning follows. In reality, the meaning, if you insist on using that word, is already written into the distribution of matter and the pattern of fluctuations long before any star shines. The first darkness is simply the period when that script is being rehearsed off stage, without spotlights. So, from the Big Bang to the first darkness, the universe moves from an almost unimaginably hot and uniform plasma to a cooler, transparent medium threaded by subtle variations in density. It passes through a moment when light decouples from matter and begins the long journey it is still on. It enters an era when gravity has room to operate, when gas can start to fall into the waiting hollows carved by dark matter. Nothing in that sequence looks like a pause. What changes is not activity, but visibility. The fire of the early plasma fades beyond our eyes. The new lights of stars and galaxies have not yet turned on. Between those two regimes, there is a span of time when the universe is radiating, moving, clumping, and evolving. But most of that evolution is happening in channels we did not evolve to see and have only recently begun to listen to. We call that span the first darkness, as if the darkness were a property of the universe. It may be more honest to say that the darkness belongs to us. If the darkness belongs to us, then so does a deeper kind of blindness. We built our picture of the universe around the thin skin of matter that happens to glow. For a long time, that skin was all we knew. Stars, nebulae, planets, bright gas, glowing disks of galaxies. The night sky looked like a scattering of lights against nothing. and so we assumed that the lights were the main story. We counted them, catalogued them, traced their motions. It was like trying to understand a city by studying only the street lamps and ignoring the roads. The first hints that something was wrong came not from poetry but from bookkeeping. In the early part of the 20th century, an astronomer named Fritz Zwicky studied a cluster of galaxies in the constellation of Coma. A cluster is a loose gravitational family, dozens or hundreds of galaxies all orbiting a common center. Zwicky measured how fast those galaxies were moving. Then he asked a simple question. Given their speeds, how much mass would the cluster need to have in order to keep them bound together by gravity? The answer did not match what he could see. If the only mass in the cluster were the stars and gas shining in his telescope, the galaxies would not be held in place. They would fly apart over cosmic time. To keep them bound, the cluster needed far more mass than the visible matter could account for. Zwicky called this missing component dark matter, a bland phrase that simply meant mass we infer from gravity but do not see. At the time, the idea mostly sat on the margin. It was easy to imagine that perhaps the missing mass was there in some ordinary form we had not yet detected. Faint stars, cold gas, compact objects too small or dim to show up in surveys. The universe could still be made out of familiar ingredients. We just needed to search more carefully. Decades later, another set of observations made that hope much harder to maintain. In the second half of the 20th century, Vera Rubin and her collaborators measured how stars and gas rotate in spiral galaxies like Andromeda. If most of the mass is concentrated in the bright central regions, you would expect the outer parts to orbit more slowly, the way planets in a solar system move more slowly as they get farther from the star. That is what Newtonian gravity predicts when mass is centrally concentrated. What Rubin found was not that. As she traced the rotation curves of these galaxies farther and farther out, the speeds did not fall off. They stayed roughly flat. Stars and gas in the outer regions were moving too fast to be held by the visible mass alone. Once again, there had to be more matter than the luminous components revealed. A great deal more. This pattern showed up in galaxy after galaxy. It was not an oddity of one system. It was a clue to a general truth. Most of the mass in a typical galaxy is not in its stars or its visible gas, but in an extended halo of unseen matter enveloping and permeating the visible disk. Other lines of evidence piled on. When clusters of galaxies pass between us and more distant background galaxies, their gravity bends the paths of light, distorting and magnifying the images behind them. This gravitational lensing effect depends directly on how much mass is present, not on whether that mass shines. Maps made from lensing, X-ray emission, and galaxy motions all point toward the same conclusion. There is a great deal of matter in the cosmos that does not emit, absorb, or reflect light in any familiar way. By the time cosmologists assembled the standard model of large-scale structure, the proportions were stark. Only a small fraction of the universe's total energy budget is in ordinary matter, the kind that forms atoms and stars and people. A larger fraction is in dark matter, which reveals itself only through gravity. An even larger fraction appears to be in something stranger still, a component called dark energy that drives the accelerated expansion of the universe. The exact numbers come from careful fits to cosmic microwave background data, galaxy surveys, and other observations. But the broad message is simple. The luminous world is a thin layer on top of a much deeper, darker foundation. Dark matter is not just a bookkeeping term anymore. It is the dominant source of gravitational scaffolding in the cosmos. Imagine pouring sand into a bowl of water and stirring it gently. Over time, the grains settle into patterns shaped by the currents in the liquid. In the universe, ordinary gas is like the sand. Dark matter is like an invisible fluid whose gravitational currents guide the motion of the gas. Where dark matter collapses into overdense regions, gas follows. Where dark matter flows into extended filaments and sheets, gas streams along those lines. Where dark matter is sparse, gas is slow to gather. Computer simulations of structure formation make this picture tangible. Start with a distribution of dark matter that includes the tiny density fluctuations imprinted in the early universe. Let it evolve under gravity in an expanding space. Over time, you see a network emerge, long filaments connecting dense nodes, with great, mostly empty regions in between. This is the cosmic web, the universe's large-scale skeleton. When you then add ordinary matter to the simulation, letting it feel the same gravitational forces, it falls into the dark matter structures. Galaxies form along the filaments, like lights strung along wires. We do not see the dark wires directly. We infer their presence from the way the lights are arranged. On scales of hundreds of millions of light-years, the cosmic web is a pattern of delicate structure and yawning emptiness. Filaments can stretch for tens of millions of light-years. The nodes where they intersect grow into rich clusters containing hundreds or thousands of galaxies. Between these structures are voids, vast regions with far fewer galaxies than the cosmic average. One of the most famous of these voids lies in the direction of the constellation Boötes. It is a roughly spherical region so large that, if you could place the Milky Way at its center, you could travel for a very long time before you encountered another bright galaxy. Observations suggest that its diameter is on the order of a few 100 million light-years. That is a scale almost impossible to integrate with everyday intuition. You could line up the Milky Way and its nearest large neighbor, Andromeda, hundreds of times across that distance. From the inside, such a void would feel like profound isolation. The sky would still hold stars, of course, because the Milky Way itself would be there. But beyond the fuzzy band of our own galaxy, the rest of the universe would be sparsely populated. Other galaxies would appear small, faint, and widely separated. It might take a long time, working only with unaided eyes and modest telescopes, to realize that you were living in an unusual region at all. From the outside, that emptiness is part of a clear pattern. Voids are the spaces between the dense threads of the cosmic web. They exist precisely because the web exists. Matter has flowed into filaments and nodes, leaving some regions drained. The Boötes void is not a failure of structure. It is a consequence of structure having formed elsewhere. On human scales, we are used to skeletons being rigid, solid, clearly outlined things, bone under flesh, frame under building. In cosmology, the skeleton is softer. It is made of gravitational potential wells and hills, regions defined by how they bend the paths of particles and light. You cannot see a potential well itself. You can only see what it does to everything that moves through it. Dark matter halos are like hollows in a field of gravity. Gas rolls into those hollows. Over time, it cools, collapses, ignites. Stars are born deep inside the potential wells, at the bottom of invisible basins. When we look at a galaxy, we see the luminous central region, the bright spiral arms, the glowing clouds of gas. We rarely picture the much larger, dimmer halo of dark matter in which all of that is embedded. To say that dark matter forms the universe's invisible skeleton is to acknowledge that most of the shaping has been done by something we only know indirectly. The positions of galaxies are tracers. The halos and filaments of dark matter are the underlying bones. In the context of the Dark Ages, this skeleton is already present before the first stars appear. The density fluctuations seeded in the early universe grow faster in the dark matter component than in ordinary gas. Because dark matter does not feel pressure or radiation in the same way, it simply falls under gravity. By the time neutral hydrogen has formed and the universe has entered its first darkness, dark matter has already begun to cluster into halos of various sizes. These halos are like invisible wells dug into the fabric of space-time. Hydrogen gas, feeling gravity, begins to flow into them. In the denser halos, gas can accumulate to the point where it becomes self-gravitating, collapsing further under its own weight. When it does, it heats up, cools, fragments, and eventually forms stars. But the decision about where that process can happen is made earlier, by the distribution of dark matter. This is why, When we map the large-scale distribution of galaxies today, we can reconstruct the statistics of the initial fluctuations in the early universe. The galaxies occupy the peaks of a landscape that was defined long before any starlight existed. The first darkness is not an absence of scaffolding. It is the time when the scaffolding is assembling itself out of dark matter, silent and unseen, while ordinary gas is still learning where to go. There is something quietly humbling in this. Most of our observational history has been built around the brightest objects: stars, supernovae, quasars, glowing gas. We defined the layout of the universe by following the light. Only later did we realize that the light is biased. It clings to the densest parts of an underlying structure. It leaves entire components of that structure practically invisible. You can feel a similar effect in a city at night. From a distance, what you notice are the lit windows, the neon signs, the pools of light under street lamps. The highways and side streets and alleys are present, but they are less obvious unless you are moving through them. You could, if you were careless, imagine that the city is mostly made of the bright spots, with darkness between them. But the actual structure, the pattern of roads and buildings and empty lots, is there whether the lights happen to be on or not. In the cosmic case, the roads are made of dark matter. The buildings, in a loose sense, are the halos. The street lamps are the galaxies. The voids are the empty lots and parks, scaled up beyond comprehension. Our languages for darkness have not caught up with this picture. We still talk about dark matter as if it were an absence, a mystery that needs to be filled with a substance. In practice, it behaves less like an emptiness and more like an organizing principle. It is the unlit framework that dictates where everything else can go. We do not yet know what dark matter is at the level of particle physics. Many candidates have been proposed: weakly interacting massive particles, axions, sterile neutrinos. More exotic possibilities. Detectors deep underground and in space have been watching for rare interactions that might reveal the identity of the dark matter particle. So far, they have not found a definitive signal. The mystery remains. But at the level of large-scale structure, dark matter is not mysterious at all. It is mapped, simulated, explored through its gravitational fingerprints. When we say that most of the matter in the universe is dark, we are not gesturing toward an absence. We are pointing at a presence that does not care about light. This distinction matters when we circle back to the idea of cosmic darkness. The Dark Ages are often drawn as if the universe were waiting for light to switch on. In reality, the universe is already profoundly organized by something that never shines. The skeleton is in place before the lamps are lit. To call that time dark is, again, to define it in terms of our own limited senses. From the standpoint of gravity, there is no darkness at all, only deeper wells and higher ridges. From the standpoint of matter, there is no pause, only motion into those wells. From the standpoint of the eventual galaxies, there is no blankness, only a quiet procession toward places where they will someday ignite. What is dark, for us, is the fact that we must reconstruct this skeleton indirectly. We cannot step outside the universe and turn on a different kind of light to see the Webb directly. We infer it from the way galaxies are arranged, from the way background images are lensed, from the bumps in the microwave background, from the statistics of clustering on various scales. We are, in a real sense, feeling our way along the bones of a vast creature whose full outline we will never quite see. The Dark Ages, viewed through this lens, are not an era when the universe lacks structure. They are the era when the universe's structure is governed almost entirely by something that does not care about visibility at all. That invisible skeleton is growing, stretching, refining itself. While our eventual eyes are not even a possibility yet, we like to think that light is what reveals the world. In cosmology, more often than not, it is gravity that does. Gravity writes the skeleton, but light is still the part of the story that reaches us. And even there, what we call absence is often just a message that has been pulled out of our narrow hearing range. Think about the simplest thing we know about light, the part that feels obvious. It moves fast, so fast that, for most of human history, it may as well have been instantaneous. You light a candle, and the room brightens. You open a door at noon and the sun floods in. The delay is too small for your senses to notice. Then you learn that light, despite its speed, is not infinitely fast. It takes time to cross distance. A few seconds from the moon, several minutes from the Sunday years, from nearby stars, millions of years from distant galaxies. The deeper you look, the older the light becomes. Now add one more step. Space itself is not static. The distances between galaxies are not fixed. On the largest scales, the universe expands, not like an explosion throwing shrapnel through air, but like a rising loaf of bread, where the dough itself swells and the raisins move apart because the space between them grows. This expansion does something subtle to light moving through it. As a photon travels across expanding space, the distance between its wave crests stretches. Its wavelength grows longer. Its color, if it was once in the visible range, shifts toward the red end of the spectrum, then beyond red into infrared, and eventually out into microwave and radio. The energy of that photon drops, not because it is losing speed, but because the fabric it is riding on is being pulled. We see this effect directly when we measure the spectra of distant galaxies. Their characteristic lines, fingerprints of the atoms in their stars and gas, are shifted toward longer wavelengths compared to the same lines measured in a laboratory on Earth. The farther away the galaxy, the larger the shift. This relationship was first described clearly in the early part of the 20th century, when Edwin Hubble and others plotted the recession speeds of galaxies against their distances and found a nearly straight line. The universe was not just big, it was expanding. What matters for our story is not just that galaxies drift apart over time, it is that light itself is stretched by the trip. Imagine a siren on a train. As the train approaches, the pitch sounds higher. As it recedes, the pitch drops. That is the Doppler effect in sound. In a similar way, as the space between a light source and an observer grows, the pitch of the light drops. Blue becomes red. Red becomes infrared. Infrared becomes microwave. So when we speak of the early universe as bright and hot, we are talking about how it was in its own frame at that time. The radiation that filled it then had much shorter wavelengths and higher energies than it does by the time it reaches us now. Over billions of years of expansion, that radiation has been stretched and cooled. The cosmic microwave background is the clearest example. At the moment when electrons and protons combined into neutral atoms and photons decoupled from matter, the universe would have glowed with a spectrum similar to that of a hot star, peaking at wavelengths that might have fallen in or near the visible range. In other words, if you could have stood there with human eyes, shielded somehow from the physical conditions, the entire sky would have been filled with a soft, intense light. As the universe expanded, that light stretched. Its peak slid from visible into infrared, from infrared into microwave. Today, billions of years later, the same radiation is still here, but its spectrum corresponds to a temperature of roughly 2.7 degrees above absolute zero. Our eyes, which respond only to a narrow band of wavelengths in the visible range, do not notice it at all. To us, the sky between stars is black. To a radio receiver tuned to the right frequencies, it is bright. Light was never gone. It just slipped out of the frame we call seeing. The same story plays out in smaller ways all across the cosmos. A star-forming region choked with dust may look dark in visible light, but in the infrared it glows, because the dust grains absorb high-energy photons and re-radiate them at longer wavelengths. A jet from a supermassive black hole may be nearly invisible in optical images, but blaze in radio. A cluster of galaxies that seems modest in starlight can be crowned with a halo of hot gas shining in X-rays. Each of these cases reminds us that dark is not a fixed category. It is a label we put on regions of the spectrum where our biological sensors are not tuned and where, for much of our history, we did not bother to build machines. Our eyes are sensitive to wavelengths from roughly 400 to 700 nanometers, a very small slice of the electromagnetic spectrum. Below that range lie ultraviolet, X-rays, and gamma rays, progressively more energetic. Above it lie infrared, microwave, and radio waves, progressively less energetic. The universe uses this entire spectrum freely. We began with only a slit. During the 20th century, we slowly widened that slit with technology. Radio telescopes revealed a sky rich with sources, pulsars, radio galaxies, the hiss of the cosmic background. Infrared observatories showed dust-enshrouded star nurseries and the redshifted light of distant galaxies. X-ray and gamma-ray observatories found violent events, supernova remnants, accreting black holes, bursts from cataclysmic explosions. Each new window made parts of the universe that had been dark suddenly visible. None of those things sprang into existence when we built the corresponding telescope. They were always there. Our instruments simply learned to listen to wavelengths our bodies ignore. Now take that lesson and apply it to the Dark Ages. After recombination, when neutral hydrogen fills space and the cosmic background light begins its long red-shifting journey, the universe is awash in radiation. But the wavelengths of that radiation are already sliding away from our visible band. As expansion continues, the background light grows cooler and softer. To human eyes, if they had existed, the sky would dim from a bright, opaque glow to black. At the same time, another form of light becomes possible. Neutral hydrogen atoms can emit and absorb photons at a very specific radio wavelength, corresponding to a small change in the relative spin of the proton and electron. This is the famous 21-centimeter line. It is weak, easily drowned out by other signals, but it is there. In principle, the distribution and motion of hydrogen gas throughout the Dark Ages is written into a shifting sea of 21-centimeter radiation, extended over a wide range of redshifts. To us, with naked eyes, this age would appear utterly dark. To a perfectly designed radio ear, it would be full of structure. Even the first stars, when they eventually form, are subject to this stretching. Their light leaves them in the ultraviolet and visible range. As it crosses the expanding universe, it shifts. By the time it reaches us today, that light from the very earliest generations of stars has been moved into the infrared. This is why a telescope like the James Webb Space Telescope was built to be sensitive in infrared wavelengths. It is not that those ancient galaxies emit infrared light originally. It is that their originally shorter wavelength photons have been stretched into that regime by cosmic expansion. From our vantage point, then, cosmic history looks like a series of handoffs. The early plasma glows in high-energy light that is later stretched into microwaves. Neutral hydrogen writes its story in radio frequencies that we are only now learning to detect. The first galaxies emit light that expansion pushes into the infrared. At every stage, radiation is present. It is just sliding down the spectrum, moving through bands where we are more or less blind. When we draw the history of the universe on a timeline, we often mark a period as dark between the bright afterglow on one side and the first visible stars on the other. That darkness is not a statement about the photons that exist. It is an admission that the photons have been stretched beyond the slice our unaided senses and early instruments could handle. What we call darkness, in this context, is simply light that has changed its pitch. There is a quiet irony here. We live on a planet whose atmosphere filters out the worst of the high-energy radiation from space, protecting DNA from being shredded by ultraviolet and more energetic photons. Our eyes evolved under this filtered sky, tuning themselves to the wavelengths that make it through most easily and carry enough energy to be useful for detailed vision without being biologically catastrophic. We call that range visible and everything else invisible, as if the cosmos agreed. It does not. It keeps broadcasting across the whole spectrum, indifferently. If you had eyes that could see radio waves, the cosmic microwave background would be a bright dome overhead. If you had eyes that could see X-rays, you would watch clusters of galaxies shining with hot gas and the surroundings of black holes flaring. If you could see in gamma rays, the sky would occasionally flash with bursts from distant cataclysms that are almost completely hidden in visible light. Our narrow band of vision is not wrong. It is just provincial. When you hear someone describe the Dark Ages as an era with no light, you can feel the weight of this provincialism. There was light, in profusion. It was just not the kind that bounces off a page in a way your retina can translate. It was too stretched, too cool, too gentle. Or it was in channels you do not naturally monitor, like the 21-centimeter whisper of hydrogen. In a sense, the universe has been cooling its own message as it expands. The radiation field everywhere is growing softer with time. The same photons that once roamed a small, dense universe with short wavelengths now drift through a vast, diffuse one with long wavelengths. The energy budget shifts from radiation-dominated to matter-dominated to something more subtle still as dark energy takes over the dynamics. But at no point does light simply disappear. It is tempting to imagine that if we could somehow ride a photon backward, reversing the expansion and watching its wavelength shrink, we would see darkness turn back into glare, microwaves turn back into visible light. The blackness between galaxies catch fire. That thought experiment is not a realistic journey, but it captures something true. Darkness is relative. It depends on the state of the light and the way you are built to receive it. What makes the Dark Ages dark, for us, is not the absence of photons. It is the absence of photons in the narrow range that we, as a species, defined as seeing. The universe kept glowing. We just step into the story much later, with eyes tuned to a very particular kind of light, and mistake our late arrival for a long, empty pause. Hidden in that supposed pause is one more voice the universe has been using all along. Not a shout, not a flash, more like a single, stubborn note held under everything else, waiting for ears that know how to listen for it. When astronomers talk about neutral hydrogen, they often mean it as background. The most common element in the cosmos. A simple atom, one proton and one electron, not yet forged into anything more elaborate. But even this simplest atom has a secret way of speaking. In its lowest energy state, the hydrogen atom can exist in two almost identical configurations. In one, the spins of the proton and the electron are aligned in the same direction. In the other, they are opposite. The configuration with aligned spins has a slightly higher energy than the one with opposite spins. Very slightly. The difference is so tiny that, for a single atom, the transition from one state to the other is incredibly rare. On average, an isolated hydrogen atom would wait tens of millions of years before flipping from the higher energy state to the lower one. When that flip does happen, the atom emits a photon with a very specific energy. Translate that energy into a wavelength of light, and you get a radio wave with a length of about 21 centimeters. Express it as a frequency, and it is about 1,420 megahertz. An absurdly precise tone in the radio part of the spectrum. In the 1940s, a Dutch astronomer, Hendrik van der Hulst, sat down with the quantum mechanics of this situation and realized that this line should exist. Neutral hydrogen, he argued, must be capable of emitting radiation at this wavelength. He also suspected it would be hard to detect. The transition is forbidden in the sense that it is extremely improbable for any one atom in any one moment. The universe would have to supply enormous numbers of atoms to make the signal visible. The universe obliged. There is so much neutral hydrogen in the Milky Way that, even with the rarity of the transition, the combined effect of countless atoms adds up to a detectable signal. In the early 1950s, Harold Ewan and Edward Purcell built a receiver to search for that 21-centimeter line from our own galaxy. They found it. That detection did not just confirm a theoretical prediction. It gave astronomers a new sense. Because the 21-centimeter line lies in the radio part of the spectrum, it can pass through dust clouds that block visible light. By tuning their instruments to that wavelength, astronomers could map the distribution and motion of neutral hydrogen throughout the Milky Way. For the first time, they could trace the spiral structure of our galaxy from the inside, following the glow of hydrogen through regions where stars were hidden. The universe, it turned out, had been humming in this key the whole time. Once you realize that hydrogen has this built-in whisper, the implications for the Dark Ages become obvious and unsettling. After recombination, when the universe is filled with neutral hydrogen and bathed in the cooling glow of the cosmic background, every atom carries the potential to emit or absorb 21-centimeter radiation. Even before the first stars ignite, The gas can interact with the background light in this narrow band, imprinting information about its temperature, density, and motion. The details are subtle, but the outline is simple. Think of three temperatures: the temperature of the background radiation, the kinetic temperature of the gas itself, and a third quantity called the spin temperature, which describes the relative population of hydrogen atoms in the higher and lower spin states. If the spin temperature is higher than the background temperature, the hydrogen will appear in emission at 21 centimeters. If the spin temperature is lower, it will appear in absorption, biting a tiny notch out of the background spectrum. Either way, the strength of that signal depends on how densely the hydrogen is distributed, how it is moving, and how it is being influenced by the first sources of light and heat. During the pure dark ages, before any stars form, the spin temperature of hydrogen tends to follow the kinetic temperature of the gas, which itself cools as the universe expands. The background radiation cools too, but more slowly. That means there is a period when the gas is colder than the background, and the 21 centimeter line should appear in absorption against the cosmic microwave glow. Later, as the first stars and black holes turn on, they heat the gas and flood space with ultraviolet photons that couple the spin temperature to the kinetic temperature in more complex ways. The 21 centimeter signal changes character, first deepening in absorption, then eventually moving into emission as the gas becomes hotter than the background. All of this makes the 21 centimeter line a powerful probe of the universe's invisible chapters. It does not care about starlight. It does not require galaxies. It only needs neutral hydrogen and a background field of radiation, both of which are present throughout the dark ages and the cosmic dawn. In principle, by measuring the sky at the right radio frequencies and watching how the 21 centimeter signal varies with frequency, you can build a three-dimensional map of hydrogen across space and time. Frequency plays the role of distance. Because the expansion of the universe redshifts the line differently depending on how far the photons have traveled. Angular position on the sky gives you direction. Combine the two, and you can slice through the dark ages like a loaf of bread, each thin sheet corresponding to hydrogen at a different cosmic epoch. In practice, it is not that clean. The 21 centimeter signal from the early universe is incredibly faint. The radio sky at the relevant frequencies is dominated by much stronger foregrounds, emissions from our own galaxy, from other galaxies, from human technology. Extracting the subtle cosmic whisper out of that roar is one of the hardest data analysis problems in observational cosmology. Still, people have been trying. Some experiments aim to measure the global signal, the sky average 21 centimeter brightness, as a function of frequency. They use relatively simple antennas, often just a single dipole or a small array, to listen to the whole sky at once. The idea is that if you can model and subtract the bright but spectrally smooth foregrounds, any residual feature that changes with frequency in the right way might be the fingerprint of the dark ages or the cosmic dawn. One of the most talked about efforts in this category is called EDGES, short for the Experiment to Detect the Global Epoch of Reionization Signature, operating from a remote site in the Australian outback to minimize human radio interference. EDGES uses carefully designed low-frequency antennas to listen in the tens to hundreds of megahertz range, where the redshifted 21 centimeter line from the early universe should appear. The instrument is deceptively simple in appearance: a metal plate, a tapered dipole, a ground screen. The complexity lies in the calibration, the modeling, the effort to account for every reflection, every cable, every irregularity in the system response. In the late 2010s, the EDGES team reported an intriguing result. They claim to have detected a broad absorption feature in the sky average spectrum, centered around a frequency that, when translated into redshift, corresponds to a time roughly a couple of 100 million years after the beginning. The depth of the absorption was larger than expected from standard models. If the signal were real and cosmological, it would suggest that the gas in the early universe was colder than predicted, or that there was an additional radio background on top of the cosmic microwave glow, or both. Immediately, alternative explanations proliferated. Perhaps dark matter particles were interacting with ordinary baryons in a way that cooled the gas more efficiently. Perhaps exotic radiation backgrounds existed. Perhaps the signal was an artifact of imperfect modeling of the foregrounds or instrumental systematics. Independent groups tried to reproduce the result with other instruments. So far, the EDGE's signal remains controversial. No other experiment has confirmed it unambiguously. Some reanalyses suggest that subtle features in the antenna response could mimic such an absorption if they are not fully accounted for. From the outside, this might look like another case of science teasing us and then retreating. A possible glimpse into the dark ages, blurred by uncertainties. But even here, in the ambiguity, the 21-centimeter line is doing exactly what it should. It is forcing us to confront just how hard it is to hear a faint cosmic whisper through the noise of our own instruments and planet. While global signal experiments listen to the average note, other projects try to map the fluctuations themselves. Arrays like the Murchison Widefield Array in Western Australia, LOFAR in Europe, and Hera in South Africa deployed dozens or hundreds of antennas spread over large areas. By correlating the signals from different pairs of antennas, they act as giant interferometers, sensitive to patterns in the sky brightness on various angular scales. Their goal is not to make pretty images, at least not yet, but to measure the power spectrum of 21-centimeter fluctuations during the epoch of reionization and, eventually, during the Dark Ages. So far, they have set upper limits. They have not yet seen a clear detection of the cosmological 21-centimeter power spectrum, but each improved limit tightens the constraints on how reionization unfolded, on how the first sources heated and ionized the gas, on how quickly the universe transformed from neutral to ionized. Looming in the near future is a much larger effort, the Square Kilometre Array. Its low-frequency component, often called SK-Low, to be built in Australian desert landscapes, is designed specifically to be sensitive to the redshifted 21-centimeter line from the Dark Ages and the Cosmic Dawn. With many thousands of antennas spread over a vast area, it aims to push beyond upper limits into actual detection and mapping. Forecasts suggest that, if it performs as planned, it will not only reconstruct the history of hydrogen, but also use that history to constrain the properties of dark matter, dark energy, and even exotic phenomena like primordial black holes, by watching how they subtly alter the timing and strength of the 21-centimeter signal. There are even proposals to build radio telescopes on the far side of the Moon, where Earth's own radio chatter would be blocked by rock, creating a quiet zone for listening to the most delicate signals from the Dark Ages. The fact that this no longer sounds like pure fantasy tells you something about how seriously cosmologists take the 21-centimeter whisper. All of this effort is directed at a line you will never see with your own eyes. That is the point. The universe's earliest chapters are written in a script that does not care about our visual preferences. Hydrogen in the Dark Ages speaks softly, in meter-long radio waves, about its temperature, its motions, its encounters with the first starlight. The background radiation from the hot young universe hums underneath, providing a reference. Dark matter shapes where the gas can go. The 21-centimeter line is the conversation between them. When we finally detect that conversation cleanly, it will not be a cinematic reveal. No single jaw-dropping image. It will be a pattern in a graph, a statistical excess above noise, a curve bending in just the right way across frequency and scale. It will tell us that throughout the so-called darkness, hydrogen was aligning and flipping its spins, absorbing and emitting, responding to faint ultraviolet light from the first stars and to the gravity of structures we still cannot see directly. In that sense, the 21-centimeter line is a perfect emblem of this whole story. A transition so unlikely in any one atom that you could sit and wait longer than human civilization has existed without seeing it happen, and yet, given enough atoms, it becomes an audible note that fills the galaxy. A signal so buried in noise that we have spent decades building ever more careful instruments just to glimpse it. And yet, once understood, capable of mapping the universe's hidden architecture, light was never truly gone. During the Dark Ages, it was stretched, softened, and encoded into channels we did not know how to use. The 21-centimeter whisper is one of those channels. It has been running in the background since long before the first human looked up and called the sky dark. If hydrogen was already whispering in the dark, then the first stars were not a single shout so much as the moment you realize the whisper has been there all along and only now begins to glow at the edges. For a while, the universe is almost entirely anonymous. Neutral hydrogen and helium drift through space, following the invisible pull of dark matter into slowly deepening wells. Nothing in that picture looks like a star. There are no bright points, no burning surfaces, no familiar constellations. Just a cooling gas, falling, colliding, and quietly rearranging itself under gravity. In those dark matter halos where the density creeps above average, the gas does not fall in smoothly. It shocks. It heats. It radiates away some of that heat and sinks deeper. Depending on the mass of the halo and the local conditions, patches of gas begin to fragment into smaller clumps. Each clump is a compromise between gravity pulling in and pressure pushing out. Once gravity wins, collapse accelerates. Deep inside one of those collapsing clouds, in a region much smaller than the halo but still vast on human scales, something new happens. As the gas density rises and the temperature climbs, the core becomes optically thick to its own radiation. Heat can no longer escape easily. Pressure rises along with temperature. The collapse slows, then stabilizes. The core becomes a protostar, a dense, hot seed surrounded by an envelope of infalling gas. From the outside, the universe still looks dark. At the center of that protostar, though, temperature and density eventually reach the point where nuclear fusion can begin. Hydrogen nuclei start to fuse into helium, releasing energy according to the same physics that powers the sun, but under far more extreme conditions. When the rate of energy generation in the core balances the tendency of gravity to compress further, the star settles into a temporary equilibrium. It switches on in the only way a star can: by burning. These first stars are not gentle. Formed in an environment with almost no heavy elements, the gas fragments differently than it does today. Heavy elements in later times act as coolants, allowing gas to radiate away energy and break into many small pieces. In the primordial gas, cooling is harder. Simulations and theoretical arguments suggest that the first generation of stars skewed toward high masses, perhaps tens or even hundreds of times the mass of the Sunday. A star that massive does not live for billions of years. It burns through its fuel rapidly and dies young. Astronomers call this hypothetical first-generation population 3, a backward naming convention that reflects how they were inferred. Population 1 stars, like the Sun, are rich in heavy elements. Population 2 stars, older and more metal-poor, inhabit galactic halos and globular clusters. Population 3 would be the metal-free ancestors, forming from pristine hydrogen and helium before any supernova had a chance to pollute the gas with heavier nuclei. We have not yet seen a population 3 star directly. They lived fast and died early, in an era so distant that their light today would be faint and pushed deep into the infrared. But we see their fingerprints everywhere. The abundance pattern of heavy elements in later generations of stars, the presence of certain isotopes, the overall chemical makeup of galaxies all point back to a time when the first furnaces lit and began forging the periodic table beyond helium. When the first massive stars ignite inside those dark matter halos, their surroundings remain opaque for a while. Photons bounce around in the dense gas. Eventually, radiation pressure carves out bubbles, pushing aside material and creating channels through which light can escape. What begins as a deeply buried fire becomes, over time, an ultraviolet lantern shining into the neutral hydrogen fog. Crucially, this does not happen everywhere at once. Different halos reach the threshold for star formation at different times. The details depend on the local density field, the mass distribution of halos, the efficiency of cooling, and the feedback from earlier generations of stars. Some regions of the universe light up earlier, others lag. The result is a patchwork, not a global switch. Imagine an endless plain covered in morning mist. Here and there, small fires are lit. Around each fire, the fog begins to thin and glow. The light does not immediately clear the entire field. Instead, islands of visibility expand slowly, sometimes merging, sometimes remaining isolated. The regions between them are still thick with mist, still dim. The early universe during the cosmic dawn looks more like that than like a bright uniform sunrise. Each new cluster of massive stars carves out an ionized bubble in the surrounding neutral hydrogen, a region where ultraviolet photons have stripped electrons from atoms, turning the gas once again into a plasma. These bubbles grow and merge over time, a messy, overlapping pattern of clearings in a fog that is being eaten from the inside out. From the perspective of hydrogen, this is a violent transition. For hundreds of millions of years, most atoms drift in a neutral state, cooling with the expansion, occasionally flipping spins and contributing to the 21-centimeter signal. Then, the first stars and black holes flood the environment with high-energy photons. Those photons travel some distance before being absorbed, heating the gas and ionizing it. The 21-centimeter whisper in those regions changes, then disappears, as neutral hydrogen gives way to plasma. From the perspective of a hypothetical observer with human eyes, if such eyes could somehow survive the radiation and physical conditions, the change would be different, but just as patchy. The sky would not go from black to uniformly filled with starlight overnight. Instead, small, intensely bright sources would appear in certain directions, while others remained dark. As more stars formed and more halos lit up, the number of visible points would increase. Faint glows from gas, illuminated by ultraviolet light, would build up. The darkness would thin unevenly. Light, in other words, does not arrive all at once. It arrives locally, in bursts, shaped by where the universe happened to stack a little more matter. There is no single moment you could point to and say, here the cosmos became bright. There is only a long, messy transition where individual lights ignite, change their surroundings and die, while others take their place. The deaths of those first massive stars are as important as their lives. Many of them end in supernova explosions, blasting heavy elements into the surrounding medium. Some may collapse directly into black holes, seeding the formation of the supermassive black holes we see at the centers of galaxies. The energy released in these deaths stirs the gas, drives winds, creates shocks. It is an early feedback loop. Star formation alters the environment in ways that can both trigger and suppress further star formation nearby. Over a few 100 million years, the cumulative effect of countless such events transforms the cosmic landscape. Regions that were once neutral become ionized. The average temperature of the intergalactic medium rises. The detailed topology of the ionized bubbles changes as they grow, merge, and eventually percolate through most of space. By the time the process known as reionization is largely complete, the universe has traded its fog of neutral hydrogen for a more transparent ionized medium, at least with respect to ultraviolet light. Even after reionization, though, the story of the first stars is not cleanly separated from what came before. The heavy elements they produced mix imperfectly. Some pockets of gas remain nearly pristine and may form second or even third generations of metal-poor stars that carry echoes of population 3 in their compositions. Others become enriched more quickly, allowing for the formation of lower mass, longer-lived stars that can survive to the present. Those survivors, old and faint, orbit in the halos of galaxies like ours, acting as fossil witnesses to conditions billions of years ago. From our vantage point in the present, we piece together this narrative from indirect evidence. We see high redshift galaxies in deep infrared images, already forming stars at a vigorous rate. We measure the absorption signatures of intervening gas in the spectra of bright background quasars, tracing how the amount of neutral hydrogen changes with time. We study extremely metal-poor stars in the Milky Way and nearby dwarf galaxies, using their chemical abundances to reconstruct the yields of the first supernovae. Each of these observational threads pulls on the same tapestry. A universe that, during its supposed dark ages, was already preparing for and then enacting a complex, spatially uneven turn toward luminosity. What never appears in that tapestry is a global blackout, followed by a single, dramatic flip of a switch. Even when we compress the story for convenience, we talk about epochs rather than instants. An epoch of recombination, a dark age, a cosmic dawn, a period of reionization. These labels are useful, but they hide the fact that every region of space has its own schedule. In some places, the first stars may have formed relatively early, creating ionized bubbles that expanded into still neutral surroundings. In others, conditions fluctuated differently, delaying star formation and leaving the hydrogen fog intact longer. Light that did not arrive all at once is another way of saying that the universe did not wait for an observer to appear before it began doing intricate, uneven work. There was no audience in those first illuminated halos, no eyes to track the turning on and off of massive stars. The entire sequence, from the first collapse of gas in a dark matter well to the last fading of a population 3 supernova remnant, unfolded without anyone to record it. We step into the story much later, armed with telescopes and equations, trying to reconstruct a dawn that, for the universe itself, was just another phase in an ongoing process. We give it names, we argue over the timing, we build instruments to measure the 21-centimeter whisper and the faint light from high redshift galaxies. But nothing we do reaches back to make that first light more or less real. If anything, the patchy, delayed arrival of starlight reinforces the same quiet message that has been running under everything in this conversation. Darkness, in cosmology, is not a single thing. It is a moving frontier between what is emitting in our chosen band and what is not, between what our instruments can currently detect and what they cannot. The first stars did not banish cosmological darkness in a single gesture. They simply added new layers of light to a universe that had never actually been empty. If the first stars were local interruptions in the dark, then the pattern of where they ignited was not random at all. It was the visible tip of a script that had been written in the universe when everything was still hot, dense, and almost featureless. Go back, not just before the first galaxies, but before neutral atoms, before the cosmic microwave background, to that early phase when the universe is a thick plasma, and even earlier when it is smaller than any picture really helps with. In that regime, quantum mechanics is not a sideshow, it is the only show. On very small scales, quantum fields cannot settle into perfectly uniform values. They fluctuate. Tiny ripples in density and energy appear and vanish, part of the restless structure of the vacuum itself. Under ordinary circumstances, these fluctuations average out. Over large volumes, high points and low points cancel. Reality looks smooth. Inflation breaks that symmetry. During inflation, space expands at an almost unimaginably rapid rate. Regions that were once in close contact are pulled far apart. Quantum fluctuations that began on microscopic scales are stretched to cosmic sizes. Once those regions are larger than a certain horizon, they can no longer communicate quickly enough to even out their differences. The ripples freeze in. The result, when inflation ends and the universe settles into a more measured expansion, is a field of tiny overdensities and underdensities laid across the whole cosmos. Slightly more matter here, slightly less there. A pattern of primordial seeds. We do not see these seeds directly. What we see, billions of years later, is what gravity did to them. Overdense regions slow their expansion, start to pull more matter in, and eventually become the homes of galaxies and clusters. Underdense regions evacuate, becoming the voids. The enormous variety of structures we observe now The so-called cosmic zoo of spirals and ellipticals and irregulars is the evolved descendant of those quantum ripples. The closest thing we have to a direct snapshot of this initial pattern is the cosmic microwave background itself. The map is deceptively simple to describe. Take the whole sky, measure the temperature of the microwave background in each direction with very high precision. Plot the slight differences. What you get is a mottled pattern. Small patches, a tiny bit warmer. Small patches, a tiny bit cooler. All arranged in a way that looks random but carries subtle statistical signatures. The typical size of the spots, the way power is distributed across different angular scales, the relative heights of the acoustic peaks in the power spectrum. All of these encode information about the composition of the universe and the nature of the initial fluctuations. Satellite missions have mapped this pattern with increasing clarity. Each step, from earlier experiments to more recent ones, sharpened the picture. By the time the Planck satellite finished its work, cosmologists could treat the microwave sky as a kind of cosmic fingerprint. From it, they inferred that only a small fraction of the universe's energy content is in ordinary matter, a larger fraction in dark matter, and the majority in dark energy, the component associated with the accelerated expansion of space. Those are big claims to be resting on tiny ripples in a background glow. Yet the same basic numbers reappear when you measure the way galaxies cluster on large scales, the way the expansion rate has changed over time, and the way structures have grown. Different lines of evidence converge on the picture that a set of quantum fluctuations, amplified by inflation, gave the universe a pattern that gravity could work with. Computer simulations take those initial conditions as a starting point. Begin with a distribution of dark matter that reflects the statistics seen in the microwave background. Let it evolve under gravity in an expanding universe. Watch as slight overdensities turn into filaments and nodes. Add gas, allow it to cool and form stars according to reasonable recipes, feed energy back into the gas when stars die. What emerges on large scales looks eerily familiar. A web of structures whose statistical properties match what galaxy surveys observe on smaller scales. In those simulations, galaxies form, merge, and transform. Some settle into disk shapes with graceful spiral arms. Others puff up into spheroidal forms, the ellipticals, often as a result of violent mergers. Some are so disturbed by interactions that they end up looking like asymmetrical knots. The diversity of real galaxies, the crowded zoo of morphologies catalogued by human volunteers in projects that invited people to classify them, is not an arbitrary gallery. It grows out of a combination of the initial conditions, the dark matter skeleton, and the messy physics of gas and star formation. In that sense, every galaxy is a fossil. Its current shape, its mass, its chemical makeup, all record the history of how those initial ripples evolved in its patch of space. Sometimes that history is dramatic enough to be obvious even without detailed modeling. In the 1990s, astronomers studying the motion of stars near the edge of the Milky Way discovered something odd. A small, faint galaxy, now called the Sagittarius Dwarf, was in the process of being torn apart by our own galaxy's gravity. Its stars were stretched into long streams, looping around the Milky Way like threads being woven into a larger fabric. This is not an isolated event. The halos of big galaxies are full of such debris. Andromeda, our nearest large neighbor, shows evidence of having swallowed several smaller galaxies over its history. Streams of stars trace their swallowed ancestors. Shells and loops around ellipticals give similar hints. The term galactic cannibalism is a bit theatrical, but the underlying idea is simple. Larger galaxies grow not only by forming new stars in their own gas, but by absorbing smaller companions. These mergers are not add-ons to the story of structure formation. They are its natural continuation. Quantum ripples determine where matter will initially be slightly overdense. Dark matter halos grow around those seeds. Small halos merge into bigger ones. Gas follows, forming stars in nested structures. Over cosmic time, a hierarchy builds up. Dwarfs feed spirals. Spirals collide and become ellipticals. clusters of galaxies accumulate at the nodes of the Webb. The cosmic zoo is, in large part, a record of this ongoing consolidation. From our vantage point, late in this process, it is easy to see the bright, elaborate outcomes and forget how little the universe had to start with. A nearly uniform hot plasma, slight perturbations, a set of physical laws, no blueprints beyond the pattern of tiny ripples and the equations governing gravity, fluid dynamics, and nuclear reactions. Even the presence of us, thinking about this, is an echo of that early pattern. The heavy elements in your body were forged in stars. Those stars formed in galaxies built in dark matter halos, seeded by quantum fluctuations. The particular arrangement of matter that led to a rocky planet in a certain orbit at a certain time in the universe's history depends on countless branching events in that gravitational cascade. It is not that everything was predetermined in any detailed sense. Small changes can produce different local outcomes. Chaos exists, but the broad strokes, the fact that there would be galaxies at all, that they would cluster, that the sky would host a cosmic zoo rather than a uniform fog, is traced back to those almost featureless initial conditions, plus a sprinkling of quantum noise. When you consider the Dark Ages in this light, the word itself begins to feel like a misdirection. The era between recombination and the first galaxies is not a blank gap between meaningful scenes. It is when gravity begins to translate quantum ripples into the first drafts of structure. Those drafts are not yet legible in visible light. They are written in density contrasts, in the slow growth of halos, in the shifting of hydrogen along filaments. Later, when you look at a deep image of the universe and see the variety of forms scattered across it, you are seeing the distant descendants of those processes. Spirals with neat arms, lenticulars, halfway between disks and ellipticals, faint dwarfs barely holding together, giant ellipticals in cluster centers. Each one is a different way of resolving the same initial constraints. The path from quantum ripples to the cosmic zoo is not a neat sequence of snapshots. It is an ongoing transformation, most of which took place out of sight, before eyes existed, and long before telescopes. The labels we use now, the categories and diagrams, are ways of compressing that transformation into something we can talk about. The universe itself did not need those labels to move from near uniform plasma to the sky you see on a clear night. By the time you call something a galaxy, the underlying story is already old. By the time you call something a galaxy, you are already looking at the end of a long chain of causes. But every so often we build a machine that lets us catch the chain a little closer to its beginning. The James Webb Space Telescope was built for that. Not to make pretty pictures, though it does that as a side effect, but to see past the comfortable middle age of the universe and into its difficult childhood. Everything about its design follows that single intention. Instead of circling Earth the way the old observatory did, Webb was sent far out, to a point in space where the gravity of Earth and the Sun balance in a useful way, a place astronomers call the second Lagrange point. It sits there in a wide halo orbit, roughly 1.5 million kilometers from us, always with the Sun, Earth, and Moon on the same side, so that a single enormous sunshield can keep its mirrors and instruments in permanent shadow. Those mirrors matter. Webb's primary mirror is made of 18 hexagonal segments, together forming a dish about 6.5 meters across, much larger than the one the older telescope carried. The bigger the mirror, the more light you can collect from faint, distant sources. The shape, the coating, the ability to adjust each segment's position with microscopic precision, all of it exists, so that the telescope can gather enough infrared photons from the edge of the observable universe to make anything like an image at all. Infrared is the key word. By the time light from the first generations of galaxies reaches us, it has been stretched by cosmic expansion out of the visible range. What left those galaxies as ultraviolet or blue light arrives as deep red or beyond, in the near and mid-infrared. If you build a telescope that only sees what human eyes could see, you will miss most of that story. So Webb was tuned from the start to wavelengths longer than what our retinas can handle, and cooled so far that its own heat would not drown out the faint signals it was meant to catch. The effort was not cheap, in money or in time. The project took roughly a quarter of a century of work by tens of thousands of people across multiple space agencies, with a total cost estimated at more than $10 billion. It survived redesigns, delays, political threats, and the constant possibility that a single failure in a single deployment mechanism could render the whole thing useless once it was far beyond the reach of any repair mission. On a December morning in the early 2020s, it finally launched atop a European-built rocket from a spaceport in French Guiana, unfolded itself in deep space like an impossibly delicate piece of origami, slid into its halo orbit, and began to cool. For months, engineers and scientists watched numbers on screens, adjusted mirrors, calibrated instruments, and waited to see whether the careful choreography of decades had actually worked. When the first full images were released the following July, one in particular became an instant shorthand for what Webb was capable of. It was a deep field centered on a galaxy cluster called SMACS 0723. To the eye, it looks like a glittering knot of galaxies with delicate arcs and smears surrounding them. To the mind, once you unpack what it represents, it is something else entirely. The patch of sky in that image is tiny, roughly the apparent size of a grain of sand held at arm's length. In that speck, Webb revealed thousands of galaxies. Some are relatively nearby in cosmic terms. Others are so distant that their light began its journey when the universe was less than 1 billion years old. Gravitational lensing by the central cluster stretches and magnifies some of the background galaxies, turning them into arcs and smears, making the whole frame look like a hall of mirrors. If you had grown used to thinking of the early universe as empty, a deep black between the hot beginning and the later rise of structure, that single image is a subtle rebuke. You choose an arbitrary piece of sky that looks blank to ground-based telescopes, and when you stare long enough in the right wavelengths, it turns out to be crowded. Again, Webb went on to do what it had been designed for, push that kind of seeing even earlier. Its infrared instruments and sensitive spectrographs began to pick out galaxies at redshifts higher than anything confirmed before, systems whose light was emitted only a few 100 million years after the beginning. Teams working on deep surveys reported galaxies whose redshift measurements, when translated into time, placed them within the first quarter of the first billion years of cosmic history. For cosmologists steeped in the standard picture, this was both exhilarating and uncomfortable. Some of these early galaxies appeared to be more massive, more luminous, or more orderly than existing models had predicted for such young times. Headlines outside the field spoke of impossible galaxies and broken cosmology. Inside the field, the mood was quieter, but not entirely calm. Part of the tension comes from how we infer the properties of galaxies at all. We do not weigh them with a scale. We see the light, measure its spectrum, and then translate that information into estimates of stellar mass and star formation rate using models of how stellar populations produce light. Those models include assumptions about how many massive stars form compared to low-mass stars, how much dust is present to absorb and re-emit light, how long star formation has been going on, and how bursty or smooth that formation is over time. Change those assumptions, and the inferred masses and ages of early galaxies can shift. What Webb was really telling us, at first, was not simply that there were too many big galaxies too early, but that the combination of our priors and our limited data had left more room for variation in the early universe than we had accounted for. As more observations accumulated, a more nuanced picture emerged. Some initial candidate galaxies turned out, after better data, not to be as extreme as first advertised. Others remained genuinely surprising but could be reconciled with adjustments to the details of star formation and feedback in high redshift environments. The core framework of a universe governed by dark matter, dark energy, and general relativity did not collapse. It flexed. This pattern is familiar in the history of astronomy. A new instrument arrives with capabilities far beyond its predecessors. Its first datasets are noisy, difficult to interpret, sitting right at the edge of what is measurable. Some early interpretations push against the current theoretical boundaries. Hype spills into popular media, Then the system settles, calibration improves. The community reworks its models, sometimes modestly, sometimes significantly, to absorb the new constraints. The universe rarely rips up its own rules. It simply reveals that our simplified versions were even more simplified than we thought. None of that dulls the shock of early light. What Webb has shown, again and again in its first years, is that the young universe is busy. Deep spectra reveal that some early galaxies are vigorously forming stars with complex chemical signatures that imply several generations of enrichment by supernovae had already taken place. Others appear strangely quiescent, already having shut down their star formation within the first billion years, the so-called sleeping galaxies that defy the expectation that everything at those times should be wildly active. Kinematic studies, mapping how gas moves inside those early systems, show not only tidy rotating disks, but also tangled, chaotic flows. Where earlier telescopes could mostly pick out the brightest, most massive, and most orderly galaxies, Webb's sensitivity has revealed a broader population. Smaller, messier systems, whose gas sloshes around in turbulent patterns, yet still manages to condense into stars. The early universe, seen this way, is not a pristine cathedral of perfect spirals appearing ahead of schedule. It is a workshop, cluttered and noisy, where gravity and feedback are still arguing over what a galaxy should look like. Even on larger scales, Webb continues the tradition of deep fields that overturn complacency. Recent mosaics capture not just one cluster with a few arcs, but thousands of galaxy groups in a single frame, some located up to around 12 billion light-years away. In those images, you can see the cosmic web in cross-section. Dense knots of interacting galaxies, filaments stretching between them, and hints of the intracluster gas and dark matter that bind these structures together. The sheer number of systems, and their diversity, is a reminder that the label early universe does not mean simple universe. All of this feeds back into the question that has been quietly running under this entire conversation. What do we really mean when we say that the universe had a dark age? From Webb's vantage point, there is no single dividing line where nothing becomes something. There is, instead, a gradual filling in of the timeline. The cosmic microwave background gives us a snapshot when the universe is only a few 100,000 years old. High redshift galaxies seen in deep infrared images show us systems a few 100 million years later, already forming stars and building structure along the dark matter web. The gaps between those anchor points are shrinking, not because the universe has changed, but because our instruments have finally learned to catch the kinds of light that have been arriving the whole time. The shock, if there is one, comes not from any single discovery, but from the cumulative effect. You grow up with a mental picture of a universe that spends a long time in silence and darkness before slowly switching on. Then you watch as telescope after telescope probes deeper and finds not emptiness, but crowded scenes that were merely too faint or too red for earlier eyes. Webb pushes that progression a little further. It does not reveal a universe that suddenly contradicts everything we thought we knew. It reveals a universe that has been active and structured earlier than our simplified stories like to admit. And sitting with that, late at night, you may notice a familiar pattern. What we keep calling darkness, in cosmology as in other parts of life, often turns out to be a temporary name for whatever lies just beyond the current reach of our senses. If darkness is often just the name we give to what lies beyond our reach, then what do we call the moment when something steps into view and seems to contradict the story we have been telling ourselves about how everything works? When the first deep results from the new telescope began to circulate in the community, there was a brief, sharp intake of breath. It was not just the raw number of early galaxies that caught attention. It was the shapes. Buried among the faint red smudges were systems that looked disturbingly familiar. Flattened, rotating structures that resembled disks, appearing at times when some people had expected only clumps and chaos. Someone gave the situation a nickname that stuck: panic at the disks. The phrase captured a feeling that did not usually make it into formal papers. In the neat diagrams of the standard model, galaxies grow hierarchically. Small things form first, collide and merge into larger structures. And over time, disks can be rebuilt from the debris if gas has time to cool and settle. Ordered, thin, extended disks, where stars follow circular orbits in a well-behaved rotation pattern, are expected to be, on average, later products of this evolution. Yet here were hints of disk-like systems already in place. When the universe was less than 1 billion years old, their light stretched into the infrared, their internal motions suggesting rotation rather than pure random turbulence. If those measurements held up, what did that say about the timeline? Outside the field, the answer was swift and dramatic. Headlines suggested that cosmology had been overturned, that the Big Bang was in trouble, that everything we thought we knew about the universe's history was wrong. It made for compelling drama. A giant, expensive telescope lifts its eyes to the sky and immediately destroys the consensus that justified building it in the first place. Inside the field, things looked different and more ordinary. People who work with the standard picture of structure formation do not treat it as a sacred text. Lambda, cold dark matter, is not a revelation. It is a model that has survived a lot of tests. It ties together the measured expansion history, the pattern in the cosmic microwave background, the large-scale distribution of galaxies, and the growth of structures over cosmic time. It could still be wrong in some deep way, but to overturn it would mean not just explaining a few early disks, but replacing an entire interlocking suite of evidence with something that fits at least as well. So, the first reaction, for many, was less panic and more curiosity sharpened by caution. How robust were the measurements that labeled those early galaxies as disks? What assumptions went into turning a faint spectral line and a blur on the sky into a statement about ordered rotation? How complete was the sample? How did selection effects bias? Which objects were being noticed and analyzed? Disks are not binary objects. A galaxy can have some degree of rotational support without being a perfect thin disk. Turbulent gas can mimic rotation in certain projections. Lopsided or clumpy systems can, when seen from some angles and with limited resolution, look more regular than they are. To classify something as a disk, you need to infer a lot from little. At the same time, theorists revisited their own expectations. Simulation results are not pure predictions from first principles. They encode choices about how to model star formation, stellar feedback, gas cooling, and the influence of black holes. When those recipes are tuned to match the properties of galaxies in the later universe, they may underrepresent the capacity for disks to form earlier under slightly different conditions. Changing those recipes within reasonable bounds can alter the population of early disks without touching the underlying cosmology. There is also the question of what exactly counts as a serious problem for a model like lambda cold dark matter. If disks form somewhat earlier, on average, than a particular set of simulations suggested, that is an invitation to refine the simulations. If there were so many massive, well-ordered disks at very early times that no plausible choice of reasonable parameters could produce them without breaking other constraints, then you would have something more interesting, a potential crack in the foundations. As the months went on and more data arrived, the sharpest edges of the panic softened. Some candidate early disks turned out to be more ambiguous once better spectra and longer exposures were taken. Others remained intriguing but not fatal. Papers that had originally carried strong claims revised their language. Follow-up simulations, run with different assumptions about gas physics, showed that under some conditions, rotating structures could indeed arise rapidly in certain halos. From a distance, this looks like ordinary scientific self-correction, and it is. But there is a deeper philosophical tension in the question people outside the field kept asking, sometimes with a trace of resentment. Was cosmology ever simply wrong? The honest answer depends on what you mean by wrong. If you mean, did cosmologists once believe things that later proved to be inaccurate, the answer is yes. There was a time when the idea of an eternal, unchanging universe was taken seriously. Before the redshifts of galaxies forced expansion onto the table, there was a time when steady-state models competed with the Big Bang, and only later did observations of the microwave background tip the balance decisively. There was a time when dark matter was treated as a bookkeeping nuisance rather than a central player, when inflation was a speculative fix rather than part of a widely used framework. But if you mean, did the whole enterprise rest on a single fragile guess that could be shattered by one image from one telescope, the answer is no. Models in cosmology, as in other parts of physics, tend to fail by degree. They become less useful, less accurate, less elegant compared to alternatives that explain more with fewer assumptions. Even when a major shift happens, much of what came before it is absorbed as a special case, an approximation that worked well in a certain regime. In that sense, Panic at the Discs was never really about whether cosmology as a whole was wrong. It was about whether the part of the story that said the early universe was relatively simple and disordered, with well-settled disks emerging later, needed to be rewritten. The answer seems to be that, yes, some of that simplicity was wishful compression. The universe was willing to build some rotating, organized systems earlier than our first attempts at modeling suggested. But that correction lives within the existing scaffolding, not outside it. You can hear a quieter message in that, if you let yourself. Our narratives about the universe lag behind the data by design. We need time to digest, to fit new pieces into old structures, or decide that the structures themselves no longer serve. In the interim, it is tempting to declare victory or disaster on the basis of the latest surprise. But underneath the swings in tone, the basic practice remains the same. Compare what you expect to what you see, and be ready to adjust, either slowly, carefully, without assuming that any single moment of shock is the final word. The early disks, whatever they ultimately mean in detail, are reminders that the cosmos does not feel bound to respect the neatness of our timelines. It will build what it can, when it can, under the constraints of its own laws. Sometimes that looks like a challenge to our models. Sometimes it looks like an invitation to make those models less provincial. Either way, the light from those young rotating galaxies left them long before we were here to be alarmed by their existence. For them, there was no panic. There was only the quiet, inevitable unfolding of gravity and gas under conditions we have only just begun to learn how to read. If the light from those young disks left them without any audience, then the same is true for the dark that came before them. The universe did not wait for language to decide what its darkness meant. Long before telescopes, long before anyone spoke of redshifts or quantum ripples, people were already trying to name the feeling of looking into a night that seemed endless. One of the oldest attempts begins with a line that has been repeated so often it is easy to stop hearing it. Darkness over the face of the deep. Notice what that line does not say. It does not say there was nothing. It does not say there was an empty void begging to be filled. It does not even say the world is waiting, frozen, for a command. It gives you two things at once: darkness and a deep, a surface you cannot see, and something moving above it. Whoever wrote those words did not have data on cosmic microwave backgrounds or dark matter webs. They did not know about neutral hydrogen, about spin temperatures, about the slow assembling of halos in the first hundreds of millions of years. But they did know what it felt like to sense that there is a difference between not seeing and there being nothing to see. Darkness, in that sentence, is a condition of the observer. The deep is a condition of whatever is there regardless. In cosmology, we have spent the last century slowly, reluctantly, being pushed toward the same distinction. We learned that the night sky is thin with stars only to our eyes, and crowded with galaxies to a better instrument. We learned that the space between those galaxies is threaded with an invisible skeleton of dark matter we cannot touch directly. We learned that the so-called dark ages were filled with hydrogen gas, humming at a wavelength our bodies will never register, and with gravity quietly building the scaffolding for everything to come. We could have called that era something else. The age of neutral gas, the time of the first halos, the quiet assembly. Instead, we reached for a word that comes from our own sensory limits: dark. We make the same move in our stories. Before something is named, before it appears in the light of language, we call it nothing. Before a person understands a period in their own life, they call it empty. Only later, when they look back and see the slow work that was happening underneath, do they admit that the emptiness was a kind of optical illusion. The old text folds that insight into its first page. Darkness over the deep. The deep is already there. Motion is already there. The sentence about light comes after. Cosmology does not use that kind of language in its equations, but the structure is similar. First, a hot, dense everything. Then, expansion, cooling, and the formation of simple nuclei. Then, recombination, decoupling, the release of the background light that still bathes us. Then, the long cooling of neutral hydrogen, the assembling of the dark matter web, the collapse of gas into halos. Only later does anything ignite that would look like light to your eyes. When you draw this as a timeline, the temptation is almost irresistible to shade that long middle chapter as black. To label it as a gap between a bright beginning and a bright present, to say, for convenience, that nothing much happened there. The universe, as far as we can tell, never agreed with that label. It moved, it clumped, it cooled. It whispered in 21-centimeter radio waves. It carried a full bath of photons left over from its early plasma state, sliding to longer wavelengths as space expanded. It heard the tug of dark matter and responded. It rehearsed the shapes of galaxies in the language of gravity long before any star marked their outlines. The darkness was never empty. It was only without witnesses. You can hear that same pattern in the way people sometimes lean on the phrase, "Let there be light." It sounds like the universe is waiting in a frozen void for a single sentence to unlock its existence. But if you put it back into the text that birthed it, it comes after the line about the deep. After a picture of waters, chaos, motion, light does not create the world there. Light makes it visible. Cosmology offers a different mechanism, but a similar hierarchy. Light does not create gravity. It does not create dark matter. It does not create the fields whose quantum fluctuations seeded structure. It illuminates what those things have already done. When Webb takes a deep field image and shows you thousands of galaxies in a patch of sky that once looked blank, it is not making those galaxies real. It is catching up to a reality that has been in place for billions of years. When a radio array spends months listening for a faint 21-centimeter absorption signal from the Dark Ages, it is not summoning that signal into being. It is tuning itself to a channel that has been broadcasting since long before anyone built antennas. In that sense, the echo between early scripture and modern cosmology is not about agreeing on the origin story. It is about noticing that both are haunted by the same human habit, confusing what we can see with what exists. The habit runs deeper than religion and science. It shows up whenever you call a stretch of your own life a blank, simply because nothing in it fits the kinds of light you have been taught to value. No obvious achievements, no dramatic joys, no disasters that at least give you a clear narrative. Just days passing, routines repeated, small adjustments made under the surface. Later, if you are unlucky, you erase those years. If you are slightly more honest, you admit that, in hindsight, they were full of slow changes that made other things possible. Hard-won skills, recovered strength, quiet decisions that did not look like decisions at the time. The deep was moving. You just did not have the right telescope pointed at it. None of this turns cosmology into allegory or ancient texts into physics. The scales are different. The ambitions are different. One speaks in equations, the other in images. The only reason to let them glance off each other here is to feel, for a moment, how persistent the intuition is that darkness and emptiness are not the same. When astronomers say that the Dark Ages were not truly dark, they mean something precise. They mean that photons were present, that gravitational fields were evolving, that hydrogen was there to emit and absorb, that the absence of visible starlight did not imply an absence of structure. They are not making a theological claim. They are pushing back against a lazy metaphor that slips too easily from language into belief. You do not have to care about ancient phrases to feel what is at stake in that pushback. If darkness is a human category, then it is negotiable. It can shrink as our senses expand. It can change meaning as our instruments become more sensitive. It can be revealed as a projection. The universe did not once stand in literal silence and void until light arrived. It was busy, indifferent to the fact that no one was around to name its activity. The same is true, uncomfortably, for most of what has happened and will happen outside the tiny window of human attention. That realization is not meant to comfort. It is meant to clear a little space. When you look up at the night and think of the Dark Ages, you are not imagining an empty screen between two bright scenes. You are thinking about a chapter of unobserved motion, full of light, that did not care whether there were eyes to meet it. When you hear the old line about darkness over the face of the deep, you can let it be what it is. An early human attempt to describe being aware of a world that exists before, beneath, and beyond your capacity to see it clearly. In both cases, the point is not that darkness hides some secret meaning that will eventually be brought into the light and make everything understandable. The point is that meaning, as we use the word, is always late. It arrives after the fact, carried by creatures who show up in the last tiny fraction of cosmic time and mistake their own thresholds for the universes. From the standpoint of hydrogen drifting through the first darkness, there is no concept of before and after light. From the standpoint of dark matter weaving its web, there is no distinction between seen and unseen. From the standpoint of an expanding space, there is no such thing as a biblical echo or a cosmological metaphor. There is only motion, interaction, cause, and consequence. We are the ones who stand at the edge of that and call some of it darkness. If we are the ones who stand at the edge and name some parts of reality darkness, then the next question is simple and impossible at once. How far are we willing to extend our ways of seeing before we admit that the word no longer fits? On the scientific side of this story, the answer looks like hardware, metal, circuitry, glass, frozen instruments staring into silence for years at a time. Future radio arrays are being planned and built to listen more carefully to the 21-centimeter whisper from hydrogen, to turn the Dark Ages from a blank band on a diagram into a textured landscape. The square-kilometer array, spread across remote deserts in the southern hemisphere, is being designed to map how neutral gas and early structure evolved across cosmic time, with a clarity that our current experiments only hint at. For cosmologists, that is not just a technical upgrade, it is a change in what counts as visible. Behind those arrays are even more ambitious ideas. A radio telescope on the far side of the moon, shielded from the noise of human transmissions by a body of rock, could in principle listen to frequencies that are currently drowned out on Earth. In that sheltered radio night, the faintest signals from the earliest times might separate themselves from foregrounds enough to be measured. If such an instrument is ever built, it will not see the Dark Ages in any human sense of the word. It will convert meter-long waves into plots and maps, patterns in data that we can then learn to read as images. Other projects look for different messengers, gravitational wave observatories, descendants of the ones that already hear the mergers of black holes and neutron stars, are being imagined and designed to operate in space, sensitive to lower frequencies. In those bands, the background murmur from countless early events, or even from processes tied to inflation itself, might be detectable. Again, no one will ever hear that hum with ears. We will see it as a residual pattern in an interferometer, a tiny correlated stretching and squeezing of space-time. Even the older tools are not finished. The infrared telescope we have been talking about has only been operating for a short time. It will keep collecting light from high redshift galaxies, from dusty star-forming regions, from atmospheres of planets around other stars, for as long as its fuel and instruments allow. What looks shocking in its first years may feel predictable later, as theory and observation settle into a new alignment. Just as the cosmic microwave background went from baffling hiss to standard reference, the patterns we are now arguing over will eventually be summarized in a few calm parameters. Each of these steps is another small extension of our senses. Not in the mystical way that phrase sometimes carries, but in a literal, engineered sense. We build detectors that respond to wavelengths our bodies ignore, to particles we never evolved to notice, to distortions in space-time that pass through us constantly without any direct sensation. Then, we teach ourselves to treat the outputs of those detectors as part of our picture of reality. We learn to say, without metaphor, that a bump in a power spectrum is a trace of the Dark Ages, that a faint dip in a sky-averaged radio curve is a sign of hydrogen colder than expected, that a whispered chirp in a gravitational wave channel is two black holes colliding in a galaxy we will never see. There is a risk, always, of turning that expansion of perception into a new arrogance. As if once we have added radio, infrared, X-rays, gravitational waves, neutrinos, we will finally have the complete set. As if the phrase unseen will eventually be retired. The lesson of the last century argues against that. Every time we add a new window, we discover that what we once called empty was already crowded. There is no particular reason to think the current suite of observables is the final one. From a more personal angle, the same pattern quietly asks a smaller question. How much of what you currently call emptiness in your own experience might be structure and motion in a band you have not yet learned to register? Periods that look like nothing happening from the narrow perspective of achievement or crisis, but which, seen through a different filter, are dense with reorganization. You do not have to dress that up as a comforting lesson. It can be more unsettling than reassuring to admit that your own sense of dark and light might be that unreliable. In cosmology, there is a phrase that gets repeated almost to the point of cliché. Absence of evidence is not evidence of absence. Usually, it is a caution against over-interpreting non-detections. Here, it doubles as a description of how the early universe has been misnamed. The Dark Ages were never an absence of photons, or fields, or structure. They were an absence of interaction with the particular detectors that happened to exist on a small planet billions of years later. What changed was not the universe. What changed is that we learned, slowly, to build better evidence. That learning does not end with a single telescope, or a single decade, or a single generation. Instruments fail. New ones take their place. Theories are adjusted, discarded, rebuilt. There will be future moments of so-called panic, when some fresh observation seems to scrape against the edges of the current framework. There will be future deep-field moments, when a piece of sky that looks empty reveals itself as a swarm of structures we had no reason to suspect. Between those peaks of drama, most of the work will be calibration, patience, and the quiet refinement of how we translate the unseen into something like a picture. If the idea that the early universe was never truly dark, only unseen, leaves a trace in you, it will probably not be a sense of closure. More likely, it will be a slightly altered awareness that every statement about nothing happening hides an assumption about what counts as something. The cosmos does not wait to be looked at before it evolves. Meaning, in the human sense, arrives late, riding on photons and data and stories, trying to catch up to events that unfolded without it. You are listening to this now, at a time when we have begun to map the first instance after the afterglow, to hear the cooled echoes of hydrogen, to glimpse the webs of matter that shaped everything that followed. There are other domains that remain dark by our current standards. Black holes and their event horizons, the nature of dark energy, the possibility of other inflationary patches beyond our observable horizon. Each one is an invitation, not to fill the darkness with fantasy, but to keep extending the narrow band of interaction on which our understanding rests. If you want to stay with that project, even just as a late-night listener, there will be more journeys, into regions where space-time folds on itself, into the strange pressure of vacuum energy, into models where our entire observable universe is only one bubble in a larger field. None of those trips will make the universe less indifferent. They will not put us at the center of anything. What they might do is make the word darkness feel a little less like a verdict, and a little more like a placeholder we are still learning to replace. There is a small, quiet violence in the way we talk about beginnings. We reach for clean breaks, before and after, dark and light, nothing and something. The universe, as far as we can tell, has never cooperated with that. It did not start in silence. It started with interaction. Fields, fluctuations, expansion, radiation, gravity. all tangled from the first fractions of a moment. It did not endure a long, empty blackout, waiting for stars to decide the story could begin. It was already writing. In wavelengths we cannot see, in particles we cannot feel, in structures that only show their outlines billions of years later. We arrived late. By the time anyone stood on a small rock around an ordinary star and named the sky night, the dark ages were long over. The first stars had lived and died. Galaxies had collided, merged, grown. The cosmic web was already in place. The background light had cooled into microwaves. Hydrogen had whispered for eons at 21 centimeters and no one had listened. Everything you have heard in this journey is, in one way or another, a consequence of that lateness. Because we are late, we mistake absence of interaction for absence of reality. We draw black bands on diagrams where our instruments fall short and call them ages of darkness. We treat visibility as a kind of existence test. If no light in our narrow band is reaching us, we talk as if nothing is there. But the dark ages were bright in microwaves, loud in gravity, alive with the motion of gas along dark matter filaments. The only thing missing was a nervous primate with a retina tuned to a tiny slice of the spectrum and enough spare time to build a telescope. The same blindness runs through smaller scales. A deep field image takes a piece of sky that looks like nothing and integrates for long hours. The result is not a miracle. It is a recalibration. This is what that nothing always was: a crowded city of galaxies, a compressed history of billions of years, a reminder that emptiness, very often, is just what lies below our threshold. If there is any lesson here, it is not that the universe is secretly kind or secretly cruel. It is that it does not negotiate with our intuitions. Light does not arrive when we are ready. Structure does not wait for witnesses. Meaning, in the human sense, comes afterward, stitched from leftovers. Delayed photons, faint radio hums, statistical patterns. Ignorance, seen from that angle, is not a moral failure. It is a boundary condition. We are finite creatures in a vast, indifferent system. Our ways of seeing are narrow. Our instruments are extensions of those limits, not escapes from them. There will always be a horizon. There will always be a before we can only infer. And yet, in that constraint, there is something like dignity. We know the dark ages were never truly dark, only because we refused to stop at "we cannot see it." We built dishes in deserts to listen for hydrogen. We launched mirrors into the cold to catch infrared from the first galaxies. We mapped tiny temperature ripples in background radiation that has been traveling since long before Earth formed. We turned empty into untranslated, one wavelength at a time. You, listening now, are part of that work whether or not you ever touch an instrument. The universe will go on being what it is either way. But every time you entertain the possibility that what you call darkness might be full of hidden structure, you are aligning yourself a little more closely with how things seem to be. That does not make the night less vast. It does not make you larger. It just lets you be slightly more honest inside your smallness. If you want to keep walking into these rooms with me, rooms that look dark until we learn a new way to see them, you know what to do. Stay with the channel. Subscribe if you have not. Leave a thought in the comments, not to win an argument, but to add one more small signal to the noise. Share this with the one person you know who might be awake at this hour, willing to sit with the idea that most of existence has unfolded unobserved. The lights are not coming on for us. They have been on, in their own language, from the beginning. All we can do is keep building better translations and keep each other company while we learn to read them.